Welcome everyone! Today, we are going to explore how to numerically solve first-order ordinary differential equations, a powerful technique for understanding systems that change over time or space. You have already seen many such equations in your physics courses, like those describing simple harmonic motion, an object in free fall, or the decay of radioactive material. Our main goal is to equip you with the skills to use Python to find approximate solutions to these equations, especially when an exact mathematical solution is difficult or impossible to obtain. We will begin by reviewing some familiar examples of first-order ODEs to build intuition. Then, we will dive into the general form these equations take and introduce a specific Python tool from the SciPy library called ODE, which is designed for this purpose. Throughout the lesson, we will work through several practical examples, showing you step-by-step how to define the problem in Python, how to call ODE, and how to interpret and visualize the results. By the end of this session, you will understand the importance of initial conditions, how to structure your Python code for ODE solving, and appreciate how this numerical approach allows us to model a wide array of real-world phenomena. When we talk about numerically solving a first-order ordinary differential equation, we are essentially looking for a set of numerical values for the dependent variable, let us say y, at discrete points of the independent variable, say x, within a specific range. To accomplish this for any first-order differential equation, a crucial piece of information is the initial condition, which is the value of lie at a starting point x naught. In Python, we primarily use the ODE function from the scipy.integrate package to find these solutions. The general form of a first-order differential equation that ODE expects is where the rate of change of y with respect to x, or dy dx, is equal to some function, let us call it r, which can depend on both y and x. For instance, in the equation describing an object falling with air resistance, where the rate of change of velocity I with respect to time t is given by g minus k times but not explicitly on t. Similarly, for the Beer-Lambert law, where the rate of change of intensity I with respect to depth z is negative alpha times I, to solve a first-order differential equation using the ODE function, there are essentially two main steps. The first step involves constructing a Python function that represents the right-hand side of your differential equation. Let us recall the general form. The rate of change of a dependent variable with respect to an independent variable equals some function, r, of the dependent and independent variables. For example, if we are solving for the velocity of an object in free fall with drag, where the rate of change of velocity, v, with respect to time t, is given by g minus k times v divided by m, we need to create a Python function. This function, let us name it r, would take the dependent variable, v in this case, and the independent variable, t, as inputs. Inside this function, you would write the expression for the right-hand side, which is g minus the quantity k divided by m, all multiplied by the dependent variable, v. The function then returns this calculated value. So, when you call this Python function with specific values for v and t, it effectively computes the value of the right-hand side of your differential equation. The second step in using ODE is to pass the Python function you created, which defines the right-hand side of your differential equation, into the ODE function itself. Along with your function, you also need to provide an initial condition and the range of the independent variable over which you want the solution. The ODE function will then return the numerical solution for the dependent variable. So the basic way to call it looks like ODE, followed by your right-hand side function, then the initial condition, and finally the array representing the points of the independent variable. This range of the independent variable, for instance, time t, would be an array of values where you want to know the solution v of t. You might create this array using a function like numpy.arrange or numpy.linspace, specifying a start time, an end time, and the number of points or the step size. The initial condition specifies the value of your dependent variable at the very first point of your independent variable's range. For example, if velocity v is 0 at time t equals 0, then your initial condition would simply be the value 0. Solving a first-order differential equation, such as finding v of t from the equation dv dt equals r of v and t, is fundamentally an integration problem. If you integrate both sides of the equation with respect to the independent variable, say from an initial time t0 to some later time t, you find that the change in the dependent variable, v of t minus v of t0, is equal to the integral of the right-hand side function r with respect to time from t0 to t. The ODE function in Python performs this integration numerically for you. It takes your defined right-hand side function r, the initial condition, which is the value of the dependent variable at the starting point, like v at t0, and the array of points for the independent variable. The initial value is absolutely mandatory because it serves as the starting point, or the seed, from which the numerical solution is built up, step by step, across the specified range of the independent variable. Without this initial anchor, the integration process cannot begin to find a unique solution. Let us look at our first concrete example. We want to numerically solve the differential equation dy dx equals x times y, with the initial condition that y equals 1 when x equals -2. We are interested in the solution for x in the range from -2 to 2.5. The Python code begins by importing necessary libraries, ODE from scipy.integrate for solving the ODE, matplotlib.pyplot for plotting, and numpy for numerical operations. Then, we define a Python function called r that takes y and x as arguments. Inside this function, it calculates x times y and returns this value, which is precisely the right-hand side of our differential equation. Next, we set up the range for our independent variable x, creating an array of values from -2 to 2.5 with a small step. We also specify our initial condition y0 as 1. Then we call ODE, passing our function r, the initial condition y0, and the array of x values. The result, which is the array of corresponding y solution values, is stored in YSOL. Finally, the code plots these y solution values against the x values and marks the initial condition point on the graph for clarity. The print statements at the end just show us the shape of the time array and a few of its values. Now let us consider another example. We want to numerically solve the differential equation dy dt equals -alpha times y plus beta times t. We are given an initial condition that y equals 100 at time t equals -1, and we want the solution for t in the range from -1 to 30. The constants alpha and beta are given as 0.3 and 1.5, respectively. The Python code structure is similar to the previous example. We import the usual libraries. The key difference here is in how we define our right-hand side function, r. This function now takes ri, t, and an additional argument, param. This param argument is a way to pass constants like alpha and beta into our function. Inside r, we unpack alpha and beta from param, and then calculate -alpha times y plus beta times t, returning this value. When we set up the problem, we define our time array tar, the initial condition y0, and then we create a tuple params containing the values of alpha and beta. When calling ODE, we pass our function r, the initial condition y0, the time array tar, and, very importantly, we use the args keyword argument to pass our params tuple. This tells ODE to supply these extra parameters to our function r. The rest of the code plots the solution YSOL against tar and highlights the initial condition. In this example, we are going to solve a slightly more complex differential equation. 5 times d y dt equals negative y plus a function u of t, with the initial condition y equals 1 at t equals 0. The function u of t is a step function. It is 0 if t is less than 10, and it is 2 if t is greater than or equal to 10. First, the code defines this step function, ut, using an if-else statement to return 0 or 2 based on the value of t. Next, it defines the right-hand side function r for our differential equation. Remember, ODE expects dy dt on the left side, so we first rearrange our equation to dy dt equals the quantity negative y plus u of t, all divided by 5. The function r takes I, t, and a parameter param, which will represent the constant 5. Inside r, it calculates the right-hand side using the current I, the value of u, t, by calling the u function, and the constant from param. We then set up our time array tar from 0 to 40, the initial condition y0 as 1, and the parameter for the constant 5. The ODE function is called with r, y 0 feet, tar, and the constant 5 passed via the args mechanism. Finally, the code plots both the input function u, t, and the resulting solution, y, t, over the time range, also marking the initial condition. Let us apply our ODE solving skills to a classic physics problem, an object in free fall subject to a drag force. The differential equation governing its velocity v as a function of time t is dv dt equals g minus the quantity k divided by m times v, where g is acceleration due to gravity, m is mass, and k is the drag coefficient. We will start the object from rest, so v of 0 equals 0. For this particular problem, an analytical solution exists, which describes the velocity approaching a terminal velocity over time. The code first defines a Python function v-theory that calculates this known analytical solution, which we can use for comparison. Then, it defines the right-hand side function r for ODE. This function r takes v, t, and a parameter tuple param containing g, m, and k. It returns g minus k divided by m times v. We then set our physical constants, g, m, k, the initial time t0, and initial velocity v0. The time array tar is created to extend a bit beyond the characteristic time to reach terminal velocity. We bundle g, m, and k into a tuple param and call ODE with our function r, initial velocity 0 feet, time array tar, and the param tuple passed via args. Finally, the code plots both the numerical solution obtained from ODE and the analytical solution from v-theory on the same graph, along with a line indicating the terminal velocity. This allows us to visually verify how well our numerical solution matches the exact one. Here we tackle another physics-based example, the Beer-Lambert law, which describes how the intensity of light decreases as it passes through a material. The differential equation is dId z equals negative alpha times I, where I is the intensity, z is the depth into the material, and alpha is an absorption coefficient. The initial condition is I of 0 equals I naught, a known initial intensity. We also know the analytical solution for this. I of z equals I naught times e to the power of negative alpha times z. The code starts by setting up initial values like I naught, alpha, and defines a relevant length scale, the penetration depth, which is 1 over alpha. A Z-array ZAR is created, spanning several penetration depths. Two Python functions are defined. I-analytical calculates the exact solution, and R defines the right-hand side, negative alpha times I, for ODE. The R function takes I, Z, and alpha as a parameter. Then, ODE is called with the R function. The initial intensity, I, 0, the ZAR array, and alpha passed as an argument. The resulting plot shows both the numerical solution from ODE and the analytical solution. To provide more physical insight, the plot also includes vertical lines at 1, 2, and 3 penetration depths, and horizontal lines at the corresponding intensity levels, which are I0 divided by E, I0 divided by E squared, and so on, illustrating the exponential decay. Following up on our Beer-Lambert law example, this section demonstrates a useful technique for visualizing and understanding the solution. Plotting with dimensionless variables. Instead of plotting the intensity I as a function of depth Z directly, we will plot the ratio of intensity to initial intensity, that is, I of Z divided by I0, against the depth Z divided by the penetration depth D. This approach normalizes the variables, making the plot independent of the specific initial intensity or the exact value of the absorption coefficient. The code generates this plot using the same analytical and ODE solutions we calculated previously. On the x-axis, we now have Z divided by D, and on the y-axis, I divided by I0. You will notice that the shape of the curve is the same, but the axes are now scaled in these dimensionless units. We again add vertical lines at dimensionless depths of 1, 2, and 3, corresponding to Z equals D, Z equals 2D, and Z equals 3D. The corresponding STOI values where these lines intersect the curve will be 1 over E, 1 over E squared, and 1 over E cubed, respectively. This type of plot is very common in physics and engineering, as it helps to reveal universal characteristics of a system's behavior. In this final coding example related to the Beer-Lambert law, we explore how to efficiently visualize the effect of changing a parameter. In this case, the absorption coefficient alpha. We want to see how the intensity profile I of Z changes for different values of alpha, say 0.1, 0.2, and 0.5, all on the same graph. The code sets up the initial conditions and the Z-array as before. The core idea here is to use a for loop. This loop iterates through a list of different alpha values. Inside the loop, for each value of alpha, we set it as the parameter to be passed to our right-hand side function R. Then, we call ODE with this specific alpha to get the intensity solution I. This solution, I, is then plotted against the Z-array, and we label each curve with its corresponding alpha value. This process repeats for each alpha in our list. After the loop finishes, we add some annotations to the plot, like lines for penetration depths based on the initial alpha value, just for reference. The result is a single plot containing multiple intensity decay curves, clearly showing that a larger alpha leads to a faster decrease in intensity with depth, which is exactly what we would expect physically. This technique of looping through parameters and plotting is very useful for comparative studies. In this lesson, we have explored the numerical solution of first-order ordinary differential equations, which are fundamental for modeling how quantities change. We learned that these equations describe the rate of change of a dependent variable as a function of itself and an independent variable. The key to solving them numerically in Python is the ODE function from the SciPy library. This process involves two main steps. First, defining a Python function that returns the value of the right-hand side of your differential equation, and second, calling ODE with this function, an essential initial condition, and the range of the independent variable over which you seek the solution. We saw through various examples, including physical systems like falling objects and light absorption, how to implement this, pass parameters, and even handle more complex function definitions. Understanding this numerical approach empowers you to analyze and predict the behavior of many dynamic systems encountered in science and engineering, especially when exact analytical solutions are out of reach, and allows you to visualize these behaviors effectively.